Hello students, in this video we'll find the equation for the Laplacian in spherical coordinates. So if we're given a function u of x, y, and z, then Laplacian of u is uxx plus uyy plus uzz. Now consider spherical coordinates. Consider x is equal to r cosine theta sine phi, y is equal to r sine theta sine phi, and z is equal to r cosine phi. So those are spherical coordinates. And recall one last thing. Recall in the previous video we were able to find the Laplacian in polar coordinates. Recall that if we just had a function u of x and y, then for this sort of a function, uxx plus uyy was equal to urr plus 1 over r ur plus 1 over r squared u theta theta. I'm going to use this formula twice to find the Laplacian in spherical coordinates. So what we're going to do is the following. We're going to let, of course, what do we know about r over here? So r over here is going to be the square root of x squared plus y squared plus z squared. And so my objective now is I'm going to define a new variable. I'm going to define s, which is just the square root of x squared plus y squared. Now if s, so now we can write down a whole bunch of different things. What is s? If s is s, x squared plus y squared, if we look at x squared plus y squared, we're going to have a common sine squared of phi, so we're going to have that s is really r sine phi. And then over here, what we're going to have is r sine phi is equal to s, so r sine phi over here turns into s's, right? So now that tells us that x is s cosine theta, and y is s sine theta. Okay, so here's what we're going to do. So now I'm going to do this in two phases. So the first phase is I'm going to say, let's look at this transformation over here. So I have x and y as functions of s and theta. So that would say that uxx, by the polar coordinate formula, plus uyy is equal to uss. So we have an ss, and then a 1 over s us, and then a 1 over s squared, and then we'll have a u theta theta, okay? I can also apply to this situation over here with z and s. So I can say that uzz plus uss is going to be equal to what? Is going to be equal to urr plus 1 over r ur, and then plus 1 over what? 1 over r squared, plus 1 over r squared, u phi. Great. Now if we add these equations together, what will we get? Let's add these equations together. We'll have uxx plus uyy plus uzz plus uss is equal to uss plus 1 over s us plus 1 over s squared u theta theta plus urr plus 1 over r ur, and then 1 over r squared u phi. Beautiful. Now notice there's a uss on both sides of the equation. Those are going to cancel out. And now I'm only left with one other term that is a us term. So I need to turn the us term into the other variables, okay? And so what does s depend on? Well, s is a function of r and phi and theta. So let's do the chain rule. So by the chain rule, that says that partial u, partial s is equal to what? And then we'll have this s squared term will be able to handle that as well. Partial u, partial s is partial u, partial r, partial s, plus partial u, partial theta, partial s, plus partial u, partial phi, partial s by the chain rule. One of these is really easy to do because s is a function of r and sine phi. So there's no theta dependence over here, so this term is gone because partial theta, partial s is nothing, there's no thetas over there. And so now let's figure out what partial r, partial s is. So if I take this equation over here, we can see any number of ways actually. So we can also write r as the square root of s squared plus z squared. So if I did partial r, partial s, what would that be? That would be a 2s over 2 square root of s squared plus z squared. Of course, the 2's will cancel out, and you're just going to have s over what? You're going to have s over s squared plus z squared. That's r. So that's going to be s over r. So this term over here is going to be an s over r. So this is going to be partial u, partial r. And then this partial r, partial s term is exactly going to be just s over r. S over r. And then what will we get? Then that term is 0. Then I have partial u, partial phi, and then partial phi, partial s. Well, we can do the derivative of this equation with respect to s. If we did so, what do we get? We get 1. Well, let's see, what's the easier way to do this over here? So the easier way to do this is to note that if I want to find partial u, partial phi, then what equation will relate the two of those things over here? Well, partial u, partial phi, from this equation over here, we're going to treat r as if we do the partial r part, if we're doing the derivative with respect to s, we treat the other variables as constant. So what we do over here is we're going to have we can use the top equation over here that says that, if I look at this equation over here, that says that s over z is equal to the tangent of phi, okay? And therefore, phi is the inverse tangent of s over z. And so if I did the derivative of this with respect to s, what do we get? So the derivative of phi with respect to s is going to be 1 over 1 plus s over z squared. And then the derivative with respect to s is going to be a 1 over z. So I have a 1 over z. So if we simplify this over here, what will we get? I'll put a z squared and a z on top. We'll really have z over z squared plus s squared. Okay? And so now what is z? Z is r cosine phi. That's r cosine of phi. Over what? And then z squared plus s squared. Well, what is z squared plus s squared? Z squared plus s squared is going to be r squared. And so when the r's cancel out, so you just go cosine phi over r. So this is going to be a cosine of phi over r. Okay? Excellent. And so now we're in a position to simplify. So what will our Laplacian be? Our Laplacian over here, uxx plus uyy plus uzz. Let's gather all the terms that we had, all the common terms we have. So we have a urr term. So I'm going to have urr plus. Now I have this term over here, this 1 over rur. And then over here on this sus term over here, what we get. So if I look at 1 over sus, that'll be right over here. So 1 over s, let's do it like this. So I have a 1 over s us is going to be what? Well, it's going to be a 1 over r ur. And then if I hit the s over here, it's going to be a plus cosine of phi over s times r. And we'll have to simplify that in a second. But the key thing to remember, that's the u phi. And so the important thing is that there's an extra 1 over rur over here. So I'm going to get a 2 over rur. Good. So that takes care of, I've handled this term over here, this term over here. I've handled one of the terms over here. I have a 1 over, then I have a 1 over r squared, u phi phi. So I'll put that over here, 1 over r squared, u phi phi. That takes care of this term over here. So I have those first two terms over here. I have a 1 over s squared, u theta theta term over here. So this 1 over, what is s squared? S squared is going to be r squared sine squared phi. So that's going to be a plus 1 over r squared sine squared phi. And then times, that was the what? That was the u theta theta term. So u theta theta. And that takes care of this term. I have this term, this term, this term, this term. And I have one of these terms over here. Now the last term over here is a cosine of phi over s times r. Now we have to figure out a formula for s times r. Well, we know that s is really what? We really know that s is r sine theta. So this expression over here is exactly just cosine of phi over, I'm going to have an r squared sine of phi. So that's just 1 over r squared. The last term over here is going to be a 1 over r squared, and that's the cotangent of phi, and that's the coefficient of what? That's the coefficient of u phi. So we have found the Laplacian in spherical coordinates by carefully differentiating using the polar form twice. Thank you very much.